Every time an athlete sets out for a run, there is a precise, invisible boundary they cross. On one side, the body hums along, comfortably clearing waste. On the other, physical stress begins to accumulate. To optimize endurance without risking overtraining, athletes divide their effort into distinct training zones, ensuring their easy runs stay genuinely easy. The upper limit of that easy aerobic zone is known as the first ventilatory threshold, or VT1. Cross this line, and the biological cost of the workout goes up. Finding that exact line usually requires a trip to a sports science lab. The standard test involves running on a treadmill while wearing a restrictive mask that analyzes every breath of oxygen and carbon dioxide. The common alternative is a field test to determine maximum heart rate. This requires pushing the body to total physical exhaustion, which disrupts normal training and recovery schedules. A recent study investigated a simpler method. Researchers demonstrated that a standard $90 consumer chest strap can pinpoint this exact threshold by tracking microscopic variations in the heart's rhythm. Researchers are now testing if this threshold can be identified without high-end clinical equipment by measuring the heart's subtle mathematical patterns. The researchers took 15 runners and equipped them with both laboratory gas exchange masks and standard Polar H10 chest straps. They put the runners through a ramp test, systematically increasing the speed and incline of the treadmill every 30 seconds until reaching total exhaustion. While the masks tracked the runner's lungs, the chest straps monitored a specific metric in the heart known as DFA alpha 1. This metric analyzes the exact milliseconds between individual heartbeats, revealing fractal patterns driven by the autonomic nervous system. At rest, the intervals are highly organized, yielding a DFA alpha 1 value around 1.5. As exercise intensity ramps up, these patterns scatter, and the metric steadily drops. The moment the value falls to 0.75, it perfectly matches the VT1 threshold recorded by the laboratory gas masks. The data from a consumer-grade wearable aligned with the clinical gold standard. The researchers then gave the exhausted runners a brief 5-minute rest period. Immediately following that recovery, the runners were forced back onto the treadmills to perform the exact same incremental ramp test a second time. This chart compares the two runs. Looking at the gas mask data, the runners hit their VT1 limit at the exact same oxygen uptake level during the second run as they did during the first. But the chest drop data tells a different story. The heart's DFA alpha 1 metric plunges rapidly, crossing the 0.75 threshold much earlier in the second run. If the respiratory system was performing identically under the same workload, there had to be a reason the heart metric broke rank. The chest strap was exposing autonomic fatigue, a deep, systemic stress on the nervous system that respiratory gases alone cannot detect. The threshold shifted under fatigue, providing the researchers with a tool to measure invisible internal exhaustion. In a fresh, non-fatigued state, runners can use this metric to map their aerobic training zones directly on the road, bypassing the lab entirely. When tracked during a standard daily warm-up, the shifting baseline acts as an early warning system for accumulating fatigue. If an athlete's DFA alpha 1 number is unusually low during an easy 5-minute jog, the body is signaling that its autonomic reserves are depleted. It is a clinical cue to back off the intensity for the day. There is a catch. This mathematical analysis relies on exact millisecond timing, making it highly sensitive to electrical noise. In fact, nearly half of the participants in this study were excluded from the final data pool due to bad signals, poor chest strap placement, or missed beats. We are moving toward network physiology, where the heart, lungs, and nervous system are tracked holistically as an interconnected web, rather than isolated parts. By monitoring the heart's mathematical correlation, we can observe the body's real-time transition between aerobic efficiency and systemic stress.